Hi guys, we already covered a little bit of 13.1 in class on Wednesday, but I wanted to kind of, re-up that. I'll include that stuff in this lecture. I guess I'll put a timestamp in the notes for the video so that you can know where to skip to if you want to. Anyway, the first thing is my approach to vectors is a little different from the standard thing where people say vectors are anything with a magnitude and a direction. I like to think vectors first very concretely as giving directions. And I don't mean that to be the same word that they use when they say a vector has direction and magnitude. I don't mean directions in terms of like going north or west, but rather complete directions of how to go from A to B. The kind of things that you tell a friend when you want them to be able to go from the store to your apartment. Okay, so, but if you're talking about things in the plane, those sorts of directions are simply how far in the x direction should you travel and how far in the y direction should you travel. So suppose I have a point here whose coordinates are 1, 2, and a second point here whose coordinates look like they're about 3, 3. Then the vector that starts at 1, 2 and goes to 3, 3 is signified by that arrow, and it involves, well, what is it? It's how much should we change the x-coordinate, going from 1 to 3, it's 2 units, and how much should we change the y-coordinate, going from 2 to 3, that's 1 unit. So we just put it in a slightly different set of decorations, right? Instead of having parentheses, we put angle braces, but we're going to go 2 in the x direction and 1 in the y direction. Closing angle brace. So that directed thing is represented this way. Now, there's a point in the plane whose numbers are 2 and 1. That would be about here, I think. And that point can sometimes be identified with that vector, or maybe it's vice versa. If you had this arrow and you just slid it over to here, it would go from the origin to 2, 1. So these two things, while they look to be different, obviously they're arrows that are in different positions. They've got different start and end points, but they are considered the same when you're talking about vectors because they're the same set of directions. It's just your starting point is different. So yeah, of course you wind up in a different place, but you did follow the same rules that somebody said. You should move 1 to the north and 2 to the east in this case. All right, so that's a little bit different, but I think it's a useful perspective in a couple of ways. Some terminology we should make sure we're all clear on. Probably makes sense though. The place where the head of the arrowhead, the pointy thing is well, it's that thing. It's where you draw the arrowhead. I don't know how much more I can say that. We generally don't draw anything at the other end, the starting point of the vector, but that's called the tail. So for this vector 2, 1, we placed it so that its tail was at 1, 2, and its head was at 3, 3. Right. There's one other piece of terminology I want to introduce now. In the book, they wait till very near the end to talk about this, but the components of a vector are just these numbers that we pulled out and said, that's really a capsule way to describe the thing. So the components are, well, for instance, the x component and the y component in this case. X component is the first number you see, y component is the second number you see between the angle braces. When are two vectors the same? When do you have two vectors that actually are indistinguishable? It doesn't have to do with where they are on the plane, right? Because, well, like I said, 2, 1 here, and this vector has also got components 2 and 1. They're the same. So a vector isn't just a single thing, it's a whole family of things. There's a whole bunch of 2, 1 vectors. You can imagine sliding this thing all over the place in the plane. Every one of those translated versions of the vector would really be the same thing. So the head and the tail, just pointed that wrong, the head and the tail don't have to do with the identity of the vector. That's just a particular instance of the vector. There's sort of two ways of denoting vectors that let you think about this. One notation, well, let's write the word notation. We can write a point followed by another point and put a vector arrow hat on top of it. That's a way to represent the vector that goes from P to Q. Now, that makes it sound like that vector really has a lot to do with P and Q, and I suppose it does, but that's just where you're defining it and where you're digging out its components. That vector, PQ, could be equal to some other vector, RS, as long as the differences between P and Q and the differences between R and S were the same. So the other way to denote a vector is just have a lowercase letter, usually lowercase, and one of those arrow hats on it. So this is sort of implying you're getting the definition of the vector from its initial and terminal points. In other words, its tail and its head. And this one is saying, somebody just told you what the components were up front. You don't need to think about the vector based anywhere in the plane. So this is sort of more generic. Okay. There's a funny thing. There's a funny thing in the standard physics-based definition of a vector as something that has magnitude and direction. And that's when the vector, in my sense of directions, would be, don't go anywhere, you're already there, stay put. What kind of instructions does the stay put vector mean? Well, it's like we're running out of space. Let's just do a quick erase. If you had that set of directions, then that means this vector. Don't change your x-coordinate position, don't change your y-coordinate position, just stay where you are. And that can be denoted by a bold-faced 0 with an arrow hat on it. So it's a special one. It's called the 0 vector. I guess that makes sense. The thing that's weird about the 0 vector when you're doing this in the standard vector is something that has a direction and a magnitude idea. Is, the 0 vector has a magnitude of 0. It's the length of the arrow it's got no length. But what's its direction? Which way is the 0 vector pointing? You're not going anywhere, so how can you talk about direction? So in that sense, I think the usual direction and magnitude approach kind of fails us for the 0 vector, but it makes perfect sense when you're thinking about this kind of directions. Just stay where you are. There's another concept I want to bring in, because the original, what's the way to say it, the original distinction we opened with on Wednesday was this, scalar versus vector. And these things are what we had said have direction and magnitude. Hope it's okay for me to abbreviate like that. And these guys have only magnitude. So almost always we will think of the scalars as being real numbers. Maybe they'll have units on them, but real, trouble spelling, numbers. Whereas vectors, because of the direction and magnitude, usually we're going to express them as tuples of real numbers. So far just a pair of real numbers, but a single real number, that's a scalar. And you can combine these things. And from this style of directions perspective, that makes reasonable sense. I mean, if the instructions to go from my house to the Quickie Mart are 1 block north, 2 blocks east, and I say, oh, just do that 3 times, where are you going to end up? 3 blocks north and 6 blocks east. So do you see that if I did 3 times, that's a terrible angle bracket. I gotta try that again. What did I just say? 2 comma 1? Well, I think I said 1 comma 2. Actually, it doesn't matter. What does it mean to multiply a number times a vector? It's almost the only thing you could expect it to mean, honestly. From your experience with algebra, it should look like this. You distribute it in. You take this multiplication and you bring it inside the vector. So you get, in this case, you get 6 comma 3 in angle braces. So you can multiply a scalar and a vector. You can multiply 2 scalars. Can you multiply a vector? Turns out, yeah, but there's more ways than one to do it. There's at least 3 that I know of. Once you have this idea of scalar multiplication, it opens up a new possible bit of terminology, which is, when do vectors have the same direction? You know, when do they actually, well, the term people use is, when are they parallel? When 2 vectors have the same direction, they're called parallel. Although they can be considered parallel and actually go opposite directions. Some people will use the term anti-parallel for that. So parallel vectors have the same direction. But they need not have the same magnitude. So you might have a vector, a little short stubby one like that, and a much longer one like that. They go in the same direction, so they're called parallel. But how does this connect with the idea of scalar multiplication? If we call this guy v, then this guy is some constant times v. In this case, in fact, the constant is bigger than 1, so you can see that c times v has gotten stretched out. If c is a negative number, then that's when you'll hear the word anti-parallel. But in the book, they don't use this term anti-parallel. They just say if it goes the opposite direction, it's still parallel. It's just the constant is a negative. All right, so what we basically looked at just now is an operation, right? A way to multiply a number and a vector, and there's more. So we want to look at operations in general. The first couple we're going to do is just adding and subtracting. So how do you add and subtract vectors? How do you add and subtract sets of directions that tell you how to go from A to B? You add by just following one set of directions and then following the other set of directions. And there's something about adding adding in particular in terms of sets of directions that kind of lends itself nicely. So again, it lends itself nicely to understanding things via that directions concept. Suppose I've got a point A here and a point B over here, and that's the vector that goes from A to B. In other words, it's the directions that tell you how many blocks north and how many blocks east should you travel to go from A to B. I might have a point C that's about up here, and that would be the vector that goes from B to C. So what do you get if you add the vector from A to B to the vector from B to C? Especially when you write it out in terms of the initial point and terminal points of the vectors, it's kind of obvious. It's just drop out the middleman. Don't make the stop at B. Go straight from A to C. And that is sometimes called the triangle picture of vector addition. But you'll more often hear people talk about the parallelogram rule for vector addition. And that's, well, it sounds weird in terms of the initial points and the terminal points that I mentioned here, but look, if you just think about it as sets of directions, we had a way to go from A to B and a way to go from B to C. Well, what if you did the way to go from B to C first and followed it up secondly with the way to go from A to B? In other words, this guy is the same vector as BC. This guy is the same vector as AB. These guys have just been parallel shifted across from one another. So this other way to add them, well, basically it's saying this. You could add BC plus AB. And in both of these cases, what you're getting is going to be equal to A to C. So that's probably not a surprise, but it's kind of good that we've rationalized it now. If you're adding vectors, it works in one of the ways that regular adding works, that it doesn't matter what order you're in. You can change the order around and you'll get the same result. This version looks really nice because you just imagine it's kind of canceling out the B's and you go straight from A to C. Here, yeah, it's mixed up, but still. If you were working generically, maybe I should do that. Rather than talking about initial points and terminal points, the tails and heads of these things, I could just have, here's a vector V, here's a vector W, here's another copy of W, and here's another copy of V. I should be more careful than I just was. Well, try multiple times, it's spelled like that. Yeah, all right, my diagram is sloppy, but well, it gets the idea across. You see that we create a parallelogram with V on two sides and W's on the other two sides, and the diagonal of that parallelogram that goes from their common tail to where their heads meet, that's V plus W. So what about subtracting? Well, you see in this parallelogram, you've got, I called it the diagonal of it. In fact, I lied a little bit because you're supposed to use the article the when there's a single thing. And aren't there two diagonals? In fact, let's make a slightly bigger picture of it. Here's a nice V, here's a nice W. I'm going to make another copy of V here. Wow. And there's another copy of W. That's it, I'll label everybody. V, V, W, W. In fact, there's 4 different vectors in the diagonals of this picture. One of them we did was this one. It goes from, sorry, it's kind of a curvy vector, but it goes from the common base point, or the common tail of these vectors to their common head. It goes that way. There's 2 more that are this way, one this way and one that way. The 2 possible ways to go across the diagonal. And then there's a fourth one rather, this way. It goes from the heads back to the tails. You see there's 4 different things here. The one that went that way, that was V plus W. The one that goes backwards against that direction, what is that? Well, that is the negative of v plus the negative of w. Because to think about the negative of a vector, it's just -1 times that vector. But it's very easy geometrically. You just take the head off of it and put it on where the tail is. Just take the arrowhead and put it at the other end, or in other words, swap its direction. So this backward version of the diagonal there is the negative of v plus the negative of w. And then these other two guys are v minus w and w minus v. You know that, well, subtraction doesn't commute, even in ordinary arithmetic. 6 minus 3 is not the same as 3 minus 6. So, which is which? Yeah, I have a hard time with this. So, one's that way, one's this way. Let me try to sort out which it is. I've already sort of talked to you about the negative of a vector. What I would like to do is say something like this, that v minus w, actually that's sort of not a real thing. There really is no subtraction. What you really want to think about is adding a negative. Which is actually how we think about subtraction with regular numbers, so it makes sense here. If you take the vector and subtract w, it's the same thing as taking the vector and adding the negative of w. Cool. Let me switch colors so that we see what the negative of w looks like. It's the red thing that goes the opposite direction as w did. So what do you get if you add v and the negative of w? You have to, again, make another parallelogram picture, but that means that you want this, negative w vector to be shifted down till its tail lines up with the head of v. So it's about like that. That's the negative of w. So if we add v and the negative of w, that result goes this way. That's, in fact, it's kind of cool that it went right through the things where I was writing it algebraically. It's this one right here. That's the one that looks like v minus w. So the other guy must be w minus v. And that's also something you can think about algebraically. The negative of this would be negative v plus w, 2 minus, we haven't gotten there yet, so we'll talk about the algebra of working with vectors in a sec. Okay, there's something, I think I've even used the term, but I didn't define it yet, so that was bad. But whenever you have a vector, it does have a magnitude. All right, so what's the magnitude of a vector? I'm going to just put some unlabeled points out here, and there's a vector v that goes between them. Because what I want to concentrate on is the components of v. Suppose v has components, actually the standard way to refer to the components of a vector is to use the same letter and then put subscripts on it. Bless me. So v has components v1, v2. Well, that means that you could think about shifting v down until it was at the origin, or its tail was at the origin. And then, it would still have components v1, v2. But more importantly now, we know the tip of it, that point, would be the point v1, v2. So the question about how long the vector is has been morphed into a question about how far is this point from the origin? What's the distance between 0, 0 and v1, v2? And that has an easy answer. It's the distance formula. I'll give you the distance formula in general. That looks like this. The distance is the square root of the two x coordinates, or the difference of the two x coordinates squared, plus the difference between the y coordinates squared. But that general version of it is not what we need because we're going from 0, 0 to v1, v2. Yeah, that's a confusing way to deal with subscripts. This one has the subscripts referring to the points. This one has the subscripts referring to the first and second position. So don't worry about the distance formula. Just scribble that out. How far is 0, 0 and v1, v2? How far apart are they? That would be the square root of v1 minus 0 squared plus v2 minus 0 squared. And that's kind of dumb to write minus 0 on both of those too. So it's the square root of the sum of the squares of the components. How do you write that? What is this magnitude? It's done like this. Use absolute values around the name of the vector, which is overloading the use of the absolute values, but that's kind of okay because if you got absolute values around a number, you know, it's the regular absolute values, and if you've got it around a vector, it means this. So for us, it's going to just be the square root of the sum of the squares of the components. It's kind of funky looking when you have subscripts and superscripts in the same expression. Also, I'm usually trying to write little serifs on the B letters so that you, well, I have to mention this. There's a tendency in stuff on vectors to use the vectors U and V as the names just of generic vectors, and I think that's a terrible choice because U and V are really easy to mix up if your handwriting is all sloppy, which is why you may have noticed I use V and W. But anyway, something that you can help is to write U and V as I've done here, where you exaggerate that downstroke part of the U and you put a little serif on the V. That way you can distinguish them better. All right, enough of that. Once you've got the notion of magnitude, or the length of a vector, there's a special category of vectors that you should think about. They're the vectors that have length 1. Why is 1 important? It's almost like by making looking at a vector of length 1, yeah, it has a magnitude, but it's this predefined value. Its magnitude is 1. It's kind of like it's purely about the direction when it's a unit vector, as they're called. So let me write a definition of unit vector. It's going to be a vector, let's just call it V, and all we need of it is that if you take its length, you get 1. Absolute values around V, you'll get 1. So do we know some unit vectors? Sure. Examples. Let's write a small list of examples. The vector that goes 1 in the x direction and 0 in the y direction. That actually has a name. People call that I. But I with a vector hat on it, so it's not like the complex numbers I. And the vector that has the 0 and the 1 switched, so 0 in the x direction, 1 in the y direction, that one is called J. But that's just 2 unit vectors. There's lots others. There's, for instance, -1, 0, and 0, -1. If you think about what I've done here, I've just created 4 vectors who all stick out along the cardinal directions in the xy plane. They look like those. But there's more, right? There's vectors that go this way that are unit vectors, or this way that are unit vectors. And if you dig back in your brain to your days of learning trigonometry and pre-calc, you'll know the names of a lot of these vectors. Like, for instance, if you're at a 45-degree angle, this would be the vector 1 over root 2, comma, 1 over root 2. or you could say the cosine and sine of 45 degrees if you like. In fact, that's a way to build up any unit vector, use the cosine and the sine functions. Getting a little ahead of ourselves there. Okay, finally, there's a table which we're going to look at. It's on page 811, but I think we're going to switch formats and I'll do a screencast first talking about the table. So this is a scan from the textbook, the table. I've mentioned the page previously. I don't have it on in my brain right now, but it's in section 13.1. We should, I don't know that you need to memorize this because I think most of these rules for vector operations will kind of just make sense. That is, they're similar to rules you know for ordinary algebra. But let's run through them and verify that. The first one, I think we've already nailed, that the sum can be done in either order. That's the commutative property for addition. The second one is saying something about temporal order, that is time order rather than, I think of spatial order as the switching of the thing, but time order is which operation do you do first. The parentheses here are saying you would add u and v first and then add w to that. Whereas on this one, it's saying add v and w first and then add u to that. So yeah, what this rule says is that that's immaterial, which any way you put parentheses around those three things, it's going to be fine. You'll get the same result. And the two of these things together mean all that you have to have is the same three vectors. It doesn't matter how they're parenthesized, and it doesn't matter what order they're in. The zero vector. Oh, by the way, I should point out something. In the textbook, you'll notice they don't have vector hats on their vectors. What they do in typeset work is to use a boldface symbol for vectors. You see how the A and C look different from the U, V, and W. So U, V, and W are going to be vectors. A and C are scalars in this. A bold-faced zero, that's a zero vector. So this is saying, well, pretty much what you would expect, that adding a zero vector to another vector doesn't change anything. It's like saying, do the directions that V says to do, and then stay put. So you just might as well forget that and stay put, because what else would that mean? This is probably in the wrong position. They first should have talked about the definition of scalar multiplication, but whatever. I guess we know that the negative of v, a minus sign in front of v, is the same thing as multiplying v by the scalar minus 1. And if you do that, you get two vectors that sort of cancel each other out. If you think about this in terms of directions, v might be how to go from your house to your friend's house. Well, minus v would be how to go from your friend's house back to your house. And so if you do first the trip to your friend's house and then the trip back to your house, you're where you started. You've actually gotten some exercise, but in the end, you just stayed put. You didn't move. Okay, so a vector and its negative adds up to 0. This is a distributive property. If you have a scalar times a vector sum, you can put that scalar on each of the vectors and then add. It's also weird that you can distribute the vector scalar product across a sum that's amongst the scalars. So if you're adding two scalars and you multiply that times a v, it looks like you distributed the v. These are slightly different. Here, the one in 5 would be the distribution of scalar multiplication across vector addition. The one in 6 would be the distribution of scalar vector multiplication across scalar addition. So there is a need for both versions. The 0 vector can be obtained by timesing any vector by 0. That's, I think, pretty obvious. And also multiplication, if you take a 0 vector and you scale it, it's not going to change it. you could stay put a million times and you're still just staying put. The multiplicative identity for scalar vector multiplication is 1. The ordinary number 1 times a vector gives you that vector. And then finally, there's a funny associative property. And I want to just comment on that a little bit. It says that A, oops, let's get, make this be visible. In fact, let me pull it out so it's sort of up in front. A times the scalar product of C with a vector V. I'm using the hats because I can't draw in bold font. It's saying that's the same thing as multiply the two scalars, A times C, and times that by the vector. And I just want to point out that this is not the associative law. It really is not. It looks like the associative law, but you'll notice that they didn't even call it the associative law. See how they use the word property in there? Yeah, so why is this not the associative law? Because when you do the associative law, like the associative law for multiplication, all the dots are the same operation. But this dot right here is a scalar vector product. That is a scalar times a vector, as is this one. But this guy over here, that's a scalar vector. This dot in the middle between A and C, that's regular old scalar. So that's a scalar times a scalar. In other words, the two dots on one side are both scalar vector products. The nature of the operations is different on the right-hand side. Still, that's a quibble, isn't it? I mean, doesn't it look like the associative law? You just changed where the parentheses are, and that's what the associative law is about. So I think for most people's purposes, they'd look at that and go, yeah, it's fine. You can just do that. All right, so that brings us to the end of fuller treatment of 13.1. And I will have some videos posted up for you also over the weekend for viewing by Monday. Actually, I should have them up Friday afternoon. So we're trying to do 2 sections on Monday, because remember, we meet twice on Monday. All right, have a great weekend. I guess I'll see you Friday. Bye.